begin with the design and estimation of a system to supply 95 watts of power to each electrical breakout point along a fence. There are 350 breakout points distributed along a 13.5-mile long fence. The system will use a 480 volts, 3-phase power supply. The critical factor is managing voltage drop over the long distance, compounded by high ambient temperatures, reaching between 120 and 128 degrees Fahrenheit during June to October. To address this, one needs to determine the circuit parameters. The power required per breakout point is 95 watts. With 350 breakout points, the total power requirement is 95 watts multiplied by 350, which equals 33.25 kilowatts. The phase voltage is 480 volts and the line voltage is 480 volts multiplied by the square root of 3, approximately 1.732, resulting in 831 volts. Next, the circuit current must be calculated. The circuit current for a line is the total power divided by the line voltage. This is 33.25 kilowatts, or 33,250 watts, divided by 831 volts, which equals 40 amps. The voltage drop calculation involves several parameters. Use a copper conductor with a cross-sectional area of 250 kcmel. At a temperature of 125 degrees Celsius, the resistance of this conductor is 0.192 ohms per mile. The total distance is 13.5 miles. The voltage drop is calculated by multiplying the circuit current of 40 amps by the distance of 13.5 miles by the resistance per mile of 0.192 ohms. This results in a voltage drop of 10.2 volts for the line. To compensate for voltage drop, determine the allowable voltage drop, which is 5% of the line voltage. This is 5% of 831 volts, which equals 41.55 volts. The calculated voltage drop of 10.2 volts is less than the allowable voltage drop of 41.55 volts. Therefore, the system can be designed with 480 volts 3-phase without needing additional voltage compensation. The high ambient temperature, between 120 and 128 degrees Fahrenheit, will increase the conductor resistance. However, copper has a low temperature coefficient of resistance, approximately 0.393 per degree Celsius. The increase in resistance due to ambient temperature is minimal and doesn't require extra compensation. Additional considerations are also required. Use rigid conduit with a minimum diameter of 1 inch to protect conductors from environmental elements. Install the conduit underground when crossing roads to prevent damage. Provide electrical boxes at each breakout point to simplify connections. Ensure proper grounding for safety. In summary, start by determining the power requirements for all breakout points and calculate the total power needed for the entire fence system. Secondly, calculate the line voltage based on the 480 volts 3-phase supply, and then determine the circuit current by dividing the total power by the line voltage. Thirdly, use the appropriate conductor size such as 250 kcmel copper, and obtain the resistance per mile at the operating temperature of 125 degrees Celsius. Then calculate the estimated voltage drop along the 13.5-mile fence. Fourthly, compare this calculated voltage drop to the maximum allowable voltage drop, which is 5% of the line voltage. Since the estimated voltage drop is well below the allowable limit, no additional voltage compensation is needed. Note that high ambient temperatures in desert climates can affect conductor resistance, but copper's low temperature coefficient minimizes this impact. Finally, remember the importance of using rigid conduit, burying the conduit under road crossings, installing electrical boxes at each breakout point, and ensuring proper grounding for safety and compliance with electrical codes. The allowable voltage drop depends on the application and local electrical codes. In many power distribution systems, a voltage drop of no more than 5% from the source to the furthest load is recommended. This helps ensure that equipment operates efficiently and avoids issues like overheating or malfunction. The National Electrical Code, or NEC, provides guidelines for voltage drop in branch circuits and feeders. It is advisable to follow these guidelines to maintain system performance and safety. Although a 5% voltage drop is a common benchmark, certain sensitive equipment may require even tighter voltage regulation. For instance, electronic devices or precision machinery might need a voltage drop of no more than 3% to function correctly. Exceeding the voltage drop limits can lead to various problems. Motors may overheat and have reduced torque, lighting systems can dim, and electronic equipment may malfunction or provide inaccurate readings. Furthermore, significant voltage drops can increase current draw, leading to higher energy consumption and potentially overloading circuits. To mitigate voltage drop, you can consider a few strategies. Firstly, increase the conductor size to reduce resistance. Secondly, shorten the circuit length, if possible, to minimize the distance over which the voltage drop occurs. Thirdly, use higher voltage levels to reduce current and, consequently, voltage drop. Fourthly, install voltage regulators or transformers to maintain voltage levels at critical points in the distribution system. Proper planning and design are crucial to managing voltage drop effectively. Accurate calculations, consideration of environmental factors, and adherence to electrical codes are essential for ensuring a reliable and efficient power distribution system, especially over long distances in challenging environments. The selection of appropriate rigid conduit is crucial for protecting electrical conductors in harsh environments. Rigid metal conduit, or RMC, is a heavy-duty option made from galvanized steel or aluminum, offering excellent protection against physical damage and corrosion. Intermediate metal conduit, or INC, is lighter than RMC but still provides good protection. Electrical metallic tubing, or IM, is a thin-walled conduit suitable for indoor use and protected outdoor locations. PVC conduit is a non-metallic option resistant to corrosion and suitable for underground or direct burial applications. Fiber-reinforced conduit, or FRC, is a lightweight, high-strength option ideal for corrosive environments and underground installations. Factors influencing conduit selection include environmental conditions such as temperature, moisture, and exposure to chemicals. Consider the degree of physical protection needed based on potential impacts or abrasions. The type of wiring and cables being used will dictate the required conduit diameter and material. Local and national electrical codes, such as the NEC, specify conduit requirements and installation practices. Installation practices for rigid conduit involve several key steps. Firstly, cutting the conduit to the required length using a pipe cutter or saw. Secondly, reaming the cut ends to remove burrs and sharp edges that could damage conductors. Thirdly, threading conduit ends using a threading tool for secure connections. Fourthly, joining conduit sections and fittings using appropriate couplings and connectors. Finally, supporting the conduit using clamps and hangers to maintain proper alignment and prevent sagging. Underground installations require specific considerations. Ensure the conduit is buried at the correct depth according to local codes, typically at least 18 inches. Use proper fittings and seals to prevent moisture and soil from entering the conduit. Consider encasing the conduit in concrete for added protection in high-traffic areas. Mark the location of the underground conduit with warning tape to prevent accidental damage during future digging. Regularly inspect and maintain the conduit system to address any signs of damage, corrosion, or loose connections. Repair or replace damaged sections promptly to prevent electrical hazards and maintain system reliability. Follow all applicable electrical codes and safety standards when working with rigid conduit to ensure a safe and compliant installation. Grounding is an essential safety measure in electrical systems, providing a low resistance path for fault currents to return to the source, thereby minimizing the risk of electric shock and equipment damage. There are several types of grounding techniques. Equipment grounding connects non-current carrying metal parts of electrical equipment to the grounding system. System grounding connects the neutral point of a power system to the ground. Grounding electrodes provide a physical connection to the earth. Ground fault circuit interrupters, or GFCIs, detect ground faults and quickly disconnect power to prevent electric shock. Proper grounding offers numerous benefits. It reduces the risk of electric shock by providing a safe path for fault currents. It protects equipment from damage by diverting fault currents away from sensitive components. It minimizes the risk of fire by quickly clearing ground faults. It improves the overall reliability and stability of the electrical system. Key components of a grounding system include grounding electrodes, which are typically copper rods, pipes, or plates buried in the earth. Grounding conductors, which are wires that connect equipment and the neutral point of the grounding electrode. Bonding jumpers, which connect metal parts of equipment together to ensure a continuous ground path. Grounding bus bars, which serve as central connection points for grounding conductors. Installation practices for grounding systems involve several steps. Firstly, install grounding electrodes in accordance with local and national codes, ensuring they are driven deep enough into the earth. Secondly, connect grounding conductors to equipment and the neutral point using appropriate connectors and methods. Thirdly, bond all metal parts of equipment together using bonding jumpers. Fourthly, test the grounding system to ensure it has a low resistance to ground, typically less than 25 ohms. Regular inspection and maintenance are essential for ensuring the effectiveness of the grounding system. Check grounding connections for corrosion or looseness. Test the resistance to ground periodically to verify the grounding system's integrity. Repair or replace any damaged or corroded components promptly. Common grounding mistakes to avoid include inadequate grounding electrode installation, improper grounding conductor connections, failure to bond metal parts of equipment, and neglecting to test the grounding system regularly. Adhering to electrical codes and standards is crucial for ensuring a safe and effective grounding system. The NEC provides detailed requirements for grounding electrical systems and equipment. Local codes may have additional requirements or variations. Following these codes and standards helps to minimize the risk of electrical hazards and ensure compliance with regulatory requirements. By implementing proper grounding techniques, you can significantly enhance the safety and reliability of electrical systems, protecting people and equipment from the dangers of electrical faults. Electrical boxes serve as protective enclosures for electrical connections, providing safety and organization in electrical systems. Different types of electrical boxes are available for various applications. Metal boxes are durable and provide good protection against physical damage. Plastic boxes are lightweight and corrosion resistant. Surface mount boxes are installed on the surface of walls or ceilings. Flush mount boxes are recessed into walls or ceilings. Weatherproof boxes are designed for outdoor use and protect against moisture and the elements. Junction boxes are used to connect multiple wires or cables. Factors to consider when selecting electrical boxes include the intended application, such as indoor or outdoor use, the number and size of wires or cables to be accommodated, the type of wiring method being used, such as conduit or cable, the environmental conditions such as moisture, temperature, and exposure to chemicals. Local and national electrical codes, which specify box requirements and installation practices. Installation practices for electrical boxes involve several key steps. Firstly, select the appropriate box size and type for the application. Secondly, mount the box securely to a wall, ceiling, or other surface using appropriate fasteners. Thirdly, install wiring and cables into the box, ensuring proper connections and grounding. Fourthly, cover the box with a faceplate or cover to protect the wiring and prevent access. Electrical boxes must comply with electrical codes and standards to ensure safety and proper installation. The NEC provides detailed requirements for electrical boxes, including box fill calculations, grounding requirements, and mounting methods. Local codes may have additional requirements or variations. Following these codes and standards helps to minimize the risk of electrical hazards and ensure compliance with regulatory requirements. Common electrical box installation mistakes to avoid include using the wrong box size or type, overcrowding boxes with too many wires, failing to properly ground boxes, and neglecting to secure boxes properly. Selecting the correct size of electrical boxes is crucial for ensuring safe and compliant installations. Box fill calculations are used to determine the maximum number of conductors, devices, and fittings that can be installed in a box. The NEC provides guidelines for box fill calculations based on the volume of the box and the size of the conductors and devices. Overcrowding boxes can lead to overheating, insulation damage, and electrical hazards. When performing box fill calculations, consider the following factors: the number and size of conductors in the box, including both insulated and bare conductors; the number and type of devices in the box, such as switches, receptacles, and dimmers; the number and type of fittings in the box, such as cable connectors and grounding connectors; the volume of the box, which is typically marked on the box itself. Use the appropriate tables and formulas in the NEC to calculate the box fill allowance for each conductor, device, and fitting. Ensure that the total box fill allowance does not exceed the volume of the box. When in doubt, use a larger box to provide additional space for wiring and connections. Proper box fill calculations help to ensure a safe and compliant electrical installation, minimizing the risk of overheating and electrical hazards. By following these guidelines and adhering to electrical codes, you can ensure that electrical boxes are properly selected, installed, and maintained, providing a safe and reliable electrical system. Regarding the ambient temperature considerations, high ambient temperatures can significantly impact the performance and safety of electrical systems. Elevated temperatures can cause conductors to overheat, leading to insulation degradation, reduced current carrying capacity, and increased voltage drop. Electrical equipment may also malfunction or experience reduced lifespan at high temperatures. To mitigate the effects of high ambient temperatures, consider the following strategies. Select conductors with higher temperature ratings, such as those with THHN or XHHW insulation. Direct conductors based on ambient temperature using the correction factors provided in the NEC Table 310.15. Use larger conductor sizes to reduce resistance and heat generation. Provide adequate ventilation and cooling for electrical equipment, such as transformers and switchgear. Install equipment in shaded areas or use enclosures with cooling systems. Regularly inspect and maintain electrical systems to identify and address potential overheating issues. The NEC provides guidance on temperature ratings and Darrington factors for conductors and equipment. Table 310.15 provides correction factors for ampacity based on ambient temperature. Follow these guidelines to ensure that conductors and equipment are operating within their safe temperature limits. Regular inspections and maintenance are essential for identifying and addressing potential overheating issues. Look for signs of insulation damage, discoloration, or melting. Check for loose connections or corroded terminals. Use thermal imaging to identify hotspots and areas of excessive heat. Repair or replace any damaged or deteriorated components promptly. High ambient temperatures can also affect the performance of electrical equipment such as transformers, motors, and generators. Transformers may experience reduced capacity and increased losses at high temperatures. Motors may overheat and have reduced torque. Generators may experience reduced output and increased wear. To mitigate these effects, follow the manufacturer's recommendations for operating temperatures and cooling requirements. Provide adequate ventilation and cooling for equipment. Use temperature monitoring devices to track equipment temperatures and identify potential problems. By carefully considering ambient temperature effects and implementing appropriate mitigation strategies, you can ensure the safe and reliable operation of electrical systems in high-temperature environments. The NEC is updated every 3 years, and it's important to use the most current edition.